In the previous video, we learned that confidence intervals are powerful methods of inference. In this video, I want to show you how to use R to construct a confidence interval. I'm going to use the same example that I used in the previous video. This script is for calculating a 95% confidence interval for the mean GRE score of education students. I should note that these are hypothetical data. I'm going to use the normal areas functions, so I need to make sure that normaldist_areas.r is in my project folder. Indeed it is. Suppose that the mean for 64 randomly selected education students on the GRE is 147. Let's store that in a variable that we call sample mean. The standard deviation of the sampling distribution of means for the GRE will be the standard deviation of GRE scores, 8.75, divided by the square root of the number of individuals in our sample, and that is 64. Let's store this in an sd.means variable. We can now form various null hypotheses and test these using our observed sample mean of 147. Let's start with 150, which is the mean for all examinees on the GRE. I'm going to store that in a variable that I've called HO for the null hypothesis. Here's the picture of a one-tailed hypothesis test. We see that the probability of a score being 147 or less is 0.00305. To obtain the p-value, we need to multiply this probability by 2 because we're going to be doing a two-sided test. It's actually easier for us to obtain the probability using p-norm and then multiplying that by 2. So I'm not going to use the norm area below function anymore. I'm going to not worry about the picture and instead just calculate the p-values and make a decision. P-norm gives us the percentile rank for any value on a normal distribution as long as we specify the mean and standard deviation of that distribution. What I'm doing here is finding the percentile rank for the sample mean, 147, on the sampling distribution, which has a mean equal to my null hypothesized mean of 150, and a standard deviation that is the standard deviation of means. This is going to give me my lower tail probability, so I'm going to store this in a variable called lowertail.prob. In order to get my two-tailed probability, I simply need to multiply lowertail.prob times 2, and that will be my p-value. The p-value is 0.006. So we must reject this hypothesis. P is less than 0.05. We now know that education students have a lower mean on the GRE than the general population of examinees. Let's try this again, setting the null hypothesis at 149. I'm going to again use the same commands I used before. The only thing that's changing is the null hypothesis. So when I run the pnorm command, it will use a new normal distribution with a new mean, but the same standard deviation, the standard deviation of means. This time the p-value is 0.067. That's greater than 0.05, so we'll retain this hypothesis of 149. Let's try 149.5. The p-value now is 0.02, so we reject the null hypothesis. Let's try 149.1. The p-value now is 0.055, so we retain the null hypothesis. You see how I can quickly do this using the same commands over and over and simply changing the null hypothesis? Let's try 149.2. The p-value is 0.04, so we reject the null hypothesis. We found our upper boundary. Now let's try 145. Note that our sample mean is above 145, so now we must use the upper tail. How does this change our formula? This means that we have to subtract p-norm from 1. Why is that? The area under the curve is 100% of the area, or a proportion of 1, and p-norm will give us the probability up to the value of interest. So to get the tail beyond that value of interest, we have to subtract p-norm from 1. Let's do that using the null hypothesis of 145. The p-value is 0.067, so we'll retain. 145 will be in our confidence interval. Now let's try 144.8. The p-value is 0.04, so we'll reject. Let's try 144.9. The p-value is 0.055, so we retain. We've found our lower boundary. We now know with 95% confidence that the mean is between 144.8 and 149.2. R made it easy to test many hypotheses in a short amount of time, using the same commands over and over, yet changing the null hypothesized value, which changes the mean of our sampling distribution.